remainder of section 1.3.1 of Griffiths E&M, talking about surface and volume integrals. So the last video talked about line integrals, and there are a couple different other types of integrals we can do. The first of which is a surface integral. So a surface integral is an integral over the surface of some shape. And we do that by taking our vector field, V, and dotting it with an infinitesimal area element, dA. Okay, so this infinitesimal area element has units of an area, and it will be the product of two different components of your differential length. So in Cartesian coordinates, we have a differential length element that is dx x hat plus dy y hat plus dz z hat. And let's say that we have a surface that exists in the xy plane, and we want to integrate over that surface. Therefore, our infinitesimal area will be the product of dx and dy. Notice I'm taking the product of dx and dy here and building something that has units of area, right? Dx has units of length, dy has units of length, and the product of those has units of area. Now you'll notice that what I wrote here is a scalar and not a vector, and what I wrote here on the left is a vector. So our infinitesimal area is a vector, so we need to prescribe a direction to that to make it a true vector. And the way this is done for closed objects specifically is that this vector points out of a surface. Okay, so it's a little bit arbitrary what the choice is for something that is a two-dimensional sheet. You can either pick something that is in the plus z hat direction or the minus z hat direction if there's no difference between an open and closed. That choice is arbitrary. But if you have some little infinitesimal patch on a sphere, the direction of that dA is going to be radially outward, in radially outward r hat direction. Okay. So for the case of this example at the top, we're just going to go ahead and say that we want that vector to be pointed in the z hat direction. You can do integrals over closed surfaces. Just like for the case of the line integral, we can go ahead and define a closed surface with this integral with the circle around it, v dot dA. Okay. So this is a little patch on our surface, and it has an area and a direction associated with it. The last thing we're going to talk about in this video is just a volume integral. You've done volume integrals before, presumably. Now we take some scalar function t. We're no longer looking at a vector, but we're taking a scalar function, taking the volume integral of that over some prescribed volume tau. All right. So the units of d tau must be units of area, or units of volume rather, and we build that by taking products of the infinitesimal lengths in our coordinate system. So in the case of Cartesian coordinates, where I have defined dx, dy, and dz, the only way to build a volume is to make the product of all three of those. So in Cartesian coordinates, that d tau becomes dx, dy, dz. And there you go.